Where we ended Thursday was looking at our energy. I believe this is exactly where we ended, and we had these 6 forms of energy. Okay. So we have heat, light, chemical, electrical, mechanical, and nuclear. And virtually everything that we do in our everyday life has to do with these forms of energy. Okay. So for instance, to function in this room, we have lights in this room. Okay. Where did we get the light from? From lights, okay. Why are the lights light? Okay. We've pumped electricity in through a little sample. Okay. Depending on what light it is, if we go to the simplest light, our actually I'm not sure what they're called. I'm going to call them incandescent, but I'm not sure that's right. Okay. Our incandescent tubes, we pump electricity through a little bit of wire or a little bit of metal. That metal then radiates that energy as light. Okay. So you've ever seen those old school lights when they go out and you can shake them and you hear something rattling?
Yeah.
What's that rattling?
That's that wire that broke.
The wire broke. That's why the light no longer works, because electricity can't pass through it. So the wire broke and that's now rattling around inside it. Okay. So our lights came from electricity. Well, where did the electricity come from? From the power grid. Where's the power grid? How is the power grid generating that power? Okay, several different ways. What are some of those ways? Okay, mechanical. Okay, which sounds to be kind of weird, but that's how most of our power is generated. It's actually mechanical. Where are we getting the mechanical energy from?
Dams.
So dams. Water running over a dam causes a turbine to move. That turbine moving generates electrical current. Okay. How else could we generate or cause that turbine to move?
Nuclear.
Okay, nuclear. Okay, so nuclear power. What is nuclear power doing to cause the turbine to move?
Heating up water.
It is boiling water. Okay, the whole point of nuclear power is to boil water. Okay, the water turns into a gas, and what does the gas do? It moves upward and passes by a turbine. So if we've funneled that gas appropriately enough, when it moves up as a nice hot gas, it causes the turbine to move. We now have electricity. Okay? How did the gas boil or form that gas? Well, that was nuclear power. Okay? We stuck nuclear power or nuclear rods into a reactor that generates enough heat to cause the water to boil. Okay? How else could we generate power? Okay? Wind. That's good. How, no one's picking like the really obvious one.
The coal one. Right?
The coal or gasoline or petroleum. Okay, what are we doing with all of those?
Burning.
Burning to generate.
Mechanical.
How are we getting the mechanical energy? No, in the power plants.
Oh,
It combusts, so we could get gas expansion. We could also tie it back up to water and cause water to boil again. Okay, with just the petroleum, it can cause a combustion, and that causes enough force to cause turbines to move. But in a lot of cases, it ties back to water boiling. Okay? So we might think about all the labs that you've done this semester, and about 3/4 of them, what did you do?
Heat something up.
And in particular, what did you heat up? Water. Okay? All of your labs have been about boiling water. Okay? Which sounds kind of boring, but that's pretty much every lab you've done was boil water. Okay? We just use that boil water to make some observation. Okay? So in each of those cases, each of those steps, okay, so if we went from the nuclear, okay, the nuclear went to mechanical, the mechanical went to electrical, the electrical went to light. Okay? Did all of the nuclear make it through? No, because when we go nuclear, what happens? Yes, it causes stuff to move, but what else did it cause? Okay. The mechanical is literally the water molecules moving by the turbine. How did you get the water molecules to move? You had to add heat. Okay. The problem is every single one of these transitions, you also generate heat. Okay. The most obvious place that you can find this is if you go through and look at your combustion car. When you drive it around for long enough, and let's say we're driving around with it in the winter, so we can't say it's the sun heating it up. okay? And you touch the hood of your car is hot. Well, why is it hot? All you're doing is converting chemical into mechanical. Why would we be worried about heat? There's no heat there. Chemical goes to mechanical. One of the byproducts of that is heat. Heat is pretty much universal. At every single one of these transitions, we're generating heat. That heat is a loss that we can't control as well, which ultimately explains the inefficiencies in our systems. So if we go through and try and change our systems, we almost always try to minimize heat. Because the more minimal the heat, the less loss we've got, because we can't trap that heat as much. Okay, so everything we're doing is about transitioning between those different forms of energy. Okay, for this class, we're primarily focused in the chemical. Okay, what happens when we do a chemical change? Okay, well, how do we know we did a chemical change?
Reaction.
How do you know a reaction happened? Okay, light. Okay, light is a form of energy, or a change in temperature, which is a form of energy. Okay? So we're looking at those energy transitions, and those energy transitions happen to help us identify that a chemical reaction has happened. Okay? So, mechanical energy, we could take a cannon, launch a cannonball out of it, that's all mechanical, because the ball is moving. Okay? Why did the ball move? Because of the explosion in the barrel. How'd you get an explosion in the barrel?
With a mix of gunpowder.
Gunpowder, oxygen, and energy to produce a chemical reaction that produces a large change in volume of gas, which launches the ball out the barrel. Okay, so cannons work because of chemistry. Okay, so chemistry is the root here. If we look at our combustion engine, that's the lower left. Okay, what's happening? We pump in fuel into the engine. Then what do? Okay, we compress it, then what do? We explode it. Okay, just like a cannonball. Our combustion engine is a sequence, depending on how many valves you've got, okay, of 4 to 12 mini cannons. We're just harnessing those cannons into rotation. Okay? So that's kind of a neat process. How do we maximize all of those changes? Well, that's what engineers go through and do and process through how we can maximize that change in energy. Okay? Far right-hand corner, how many people are in biology? Or taken biology? Let's try that. That's a little bit better. Okay? Have you heard of ATP? What was ATP? Oh, it's just energy. No, it's not energy. ATP is a chemical compound that looks like the structure drawn here. Okay? What does ATP get converted into? ADP, which is the compound drawn underneath it. Okay? And somehow energy just appears. Okay? So we know it as energy. Well, what changed to go from ATP to ADP? And don't tell me T to D. That's roughly true, but let's get a little better than that. Okay? If we compare between these, we lost a single phosphorus and the oxygens with it. If we combine phosphorus with 4 oxygens, we now have phosphate, okay, one of our complex ions. The loss or breaking of that bond happens to release a bunch of energy. That energy happens to match most of the chemical reactions that our body goes through and produces. So ATP is the perfect currency to go through and transfer that energy. Okay. We could have picked something like glucose and thrown glucose in there and said, okay, we'll break one of the bonds in glucose. Okay. That works. We actually do that to produce ATP. But the amount of energy produced by that ends up being fairly large if we did it all instantaneously. Okay. Which would mean if we did it instantly, what happens? We explode. That's not particularly fun. So we want to control the explosion. We control the explosion by dropping the amount of energy and only breaking certain bonds, okay, at certain particular times, so that the biological system can trap that energy, much like what we're doing at a larger scale when we do nuclear to boil water. Okay? That generates energy. It also generates light. So every time we want to lighten the room, we just detonate a nuclear bomb. probably a bit excessive. We want to control that energy. Right? So we adjust how we make those transitions. Kind of makes sense? Okay. So let's bring energy in and look at our phases. Okay? So we have 3 phases up there. What can you tell me about those phases? How do you know it's solid, liquid, gas? And which one's the solid? Is this one the solid? No, okay.
The density of
The grade,
That one's a solid, followed by
water.
liquid. Why'd you say water?
Because
I know why you said water. I'm just being a jerk. Why'd you say water? Because it's blue. Yeah. It's not necessarily water. That's okay. Okay, so we're solid, liquid, gas. Okay? What's happening as we move from a solid to a liquid to a gas? Okay? We had to add energy in. What is that energy going to do?
To make it more active.
Okay? It makes the molecules move more. The more they move, the more compressibility we get. How do we get compressibility? What is compressibility? Yeah, pushing things together. What happens to the white space when we move from a solid to a liquid? I get more white space. Why is there more white space? The molecules are moving around. They're bumping against each other, pushing each other apart. Eventually, as I continue to add energy, what happens? They now push so hard against each other that what do? And by turning into a gas, they entirely break away from each other. And we now have gases. Notice, what do we have in the gas?
lots of ways.
Lots of white space. What else is happening to our particles?
Bouncing around.
They're moving a whole lot more. Okay? So we get this concept of KE. KE being kinetic energy. Kinetic, so has anybody studied kinesiology? Seriously, nobody? What is kinesiology? Anybody know that? The study of movement, usually related to the human body. So what is kinetic energy? The energy associated with movement. So what happened to the kinetic energy of our particles as we move from solid to liquid to gas? We got more energy and more movement. So the kinetic energy increased. What happened to the temperature? It also increased. What does that mean about kinetic energy with respect to temperature? They're directly related. An increase in temperature means an increase in kinetic energy. Okay? This is a fun little question, which I find particularly irritating depending on the level we look at, but let's just go ahead and do it. Do all phases have kinetic energy? Okay, is this table moving? Okay, and therein lies kind of the issue with this. Okay, our solids do have kinetic energy. They are constantly moving, but that movement is really, really, really small, not visible to the human eye. So we don't see that motion. Okay? So if we zoom out far enough and think about this on the human scale, we tend to say that our solids have no kinetic energy. I'm not a big fan of that because they do have some, but it's very, very small. So a very small amount of kinetic energy. What does that mean about the movement of solids? Very, very, very small. Okay, so we don't see solids moving a lot. Okay, what happens when we move to a liquid? Okay, we get a little bit more movement within our liquids. What happens when we move to a gas? A lot more. So what's the difference between a liquid and gas? Because we could just say, well, it's a lot more movement versus not a lot of movement, versus no movement. But we said the solid has some movement. The gas has a lot. The liquid's somewhere in between. I want to be able to describe that liquid.
Liquid's closer to a solid than it is to gas.
Okay.
Did you say gas has the most kinetic energy?
Gas has the most kinetic energy. I want you to define liquid. I want to define liquid without using gas.
Liquid has more kinetic energy than solid.
I want to define liquid without using solid.
Liquid has kinetic energy.
They all have kinetic energy, so that doesn't allow me to differentiate. Okay, the kinetic energy is tied back to movement. Okay? Do gases have a restriction on the movement?
No.
No, they are constantly moving everywhere. There's nothing holding them back from moving. Do solids have a restriction on movement? Yes, it's virtually no movement. So what's liquid then? Some type of restriction of movement. Okay? So liquids exhibit restricted movement, but it is still movement. Does that make sense? Okay. For those of you that have started studying for the final, you might have looked at the practice exam. And if you looked at the practice exam, you might understand why I just went through that bit of a silly question. It is on there, yes. Okay. So, our energy and chemical changes. So chemical energy is transformed from one form to another. So if I take water and I add electrical energy into it, okay, I can turn water into oxygen and hydrogen. Well, why would I do that? Why would I want oxygen and hydrogen?
You want to produce oxygen in certain situations?
I'm going to argue that it's not necessarily the production. Well, never mind. I know where you're coming from. The production of the oxygen tends to be less important for us on a daily basis because there's abundance of oxygen with where we're located. And for those of you that don't know Khalid's background, where is there not an abundance of oxygen for us? In a submarine. Okay. So yes, we might want oxygen produced in a submarine so that we could breathe. Okay. But because I'm focused, of course, on the ground where there's air, I'm less concerned about the oxygen, I'm more concerned about the hydrogen. What could I do with the hydrogen? We have hydrogen-fueled vehicles. Okay, hydrogen fuel cells. They're talking about hydrogen gas. And what happens when I react the hydrogen gas with the oxygen gas? I form water. That's a phenomenal waste product because now I'm just producing water. Well, I need water. That's good. But at the same time, because I've had to put energy in to get the hydrogen, when I turn it back into water, what happens? I can release that energy. Where do I release that energy to? An engine to cause mechanical motion. So I could use the production of hydrogen gas to now make a fuel to go through and have my car move faster, or not necessarily move faster, but have my car move, and the only byproduct now is water. So when you hear about hydrogen fuel cars, everybody goes, oh, well, they're fantastic, because this is what they're looking at. You take hydrogen, you react with oxygen's everywhere, that's not a big deal. I react those and I make water. Fantastic! That is the cleanest source of energy that we could possibly imagine. All we produce is water. Where did you get the hydrogen?
How did you separate them to begin with?
We got the hydrogen from water. How did we get it from water? What did we have to do? We had to add electrical energy into it. Well, where did you get the electrical energy from?
From other energy sources.
From a petroleum-based power plant? That was not a good trade. Okay? Cars are actually fairly more efficient than that system, and it's better to actually just burn straight gasoline than it is to make hydrogen, at least if we're using petroleum for our electrical energy. Could we improve this system? Instead of getting our electrical energy from petroleum, go from solar, go from wind, okay? Go from hydroelectric, from dams, where you're just getting water falling. Okay? So taking advantage of the natural system as opposed to pulling in a chemical source of energy. Okay? And that becomes tricky because we don't have that infrastructure here, which then makes hydrogen fuel cells not really relevant.
What do you do with hydrogen? What do they do?
Hydrogen bombs are talking about a different process, and we can evaluate that after class. It's outside the scope of what we're looking at here. Okay. Yeah, we try to avoid bombs, particularly highly dangerous bombs. Okay. Critical thinking. Okay. Just because this is an interesting question. Is it better to fill your gas tank in the cool morning or the warm afternoon?
Cool morning.
Okay. Why the cool morning?
Because you can get more closer to get. Yeah.
Okay? Since it's cool, what happened to the kinetic energy of your particles? It dropped, which then means you are
Have a higher density.
a higher density. So when you measure out the volume of your gas, you're getting a larger mass of the gas. And when we talk about our cars functioning, what we're concerned about is the individual gas particles, not their volume, because I could care less about the volume. I care about the chemical energy stored in those molecules. So the mass is the most important thing to me. Okay? Unfortunately, we measure by volume. So if it's cooler, okay, I'm now slightly more dense, and great, I get more gas from it. Okay? What is the difference in density? We're not looking at a liquid to a gas, because when we go pump out gasoline, it's not a gas, it's a liquid. Okay, so we're talking about a liquid at 100 degrees Celsius, not 100 degrees Celsius. Let's try Fahrenheit. 100 degrees Fahrenheit versus a liquid at, say, 70 degrees Fahrenheit. How much of a difference in the density is there for that same liquid? So tiny. Yes, you are saving money, don't get me wrong. But per tank of gas, it's something like a third of a penny, okay, that you're saving by by filling up in the cool morning. So if you do it for your lifetime, okay, and you spend lots of money on gas, maybe you save across your lifetime $10, right? Okay? Well, it's still $10. I'm gonna save that. Because some people have brought that argument up. You have higher odds of walking into the gas station, walking around the gas station and finding loose change and making more money that way than by filling up your car in the cool morning.
But you don't have to sweat your butt off if you're putting that
It's the
in.
cool morning,
Right.
cool morning.
Cool morning, you aren't sweating. Okay? Just putting it out there because that thing gets floated out. It's kind of an interesting concept. At first I was like, oh, that's cool, I'm always going to do that. And then I thought about it. I was like, yeah, it was kind of dumb. Okay? So, which now gets us into chapter 8 and 9. Okay? So there was a question on the exam, I believe it was B, which talks about moles and grams and all of that. Okay? And it usually causes students to freak out. Okay? It shouldn't cause any freak out at all whatsoever, because you have all of the conversions there. If you have a conversion process, you just use your conversions. If you don't have a process, you don't know what those units mean, which means you can't solve the question. Okay? So what we're trying to get at with that particular question on the exam is use your conversions and trust the process. You get the correct answer. If you don't have a process, or if your process was to get feet to inches, or let's try inches to feet, I just divide by 12, that's not a process, that's an algorithm. Okay? You've removed all of the process logic because you don't want to think about the calculation anymore. Okay? What you should be at by the end of this semester with doing conversions, okay, you should be like, I don't know how to convert inches into feet. I have to write it down. Okay? For those of you who think that's silly, why would you ever have to write that down? I'm aware of, for sure, at least 2 people on this campus that need to write down that conversion. I happen to be one of them. Okay? A math teacher happens to be the other one that I'm fully aware of. Neither of us can do the conversion from inches to feet without writing it down. Okay? And while that seems silly, we trust the process so much that we haven't bothered to memorize any conversion. If you trust the process, it takes you through. You guys did very well on the exam, so as a whole, you guys are following that process. Okay? If you go back and look at your show your work and you aren't getting points there, it's because you aren't following a solid process. Okay? So work on that process, because we're about to move into units that you can't physically comprehend, and because of that, you can't do a simple conversion. Okay? Kind of makes sense? Okay. So just as a warm-up, what is our process? What do we do?
What do we want?
Okay, what do we want? So in this question, what do we want? Okay. We want the mass in micrograms. Mass of micrograms of what? Of aspirin. Does anybody want to write out aspirin? No. So we want to come up with an abbreviation. I used ASP, and we talked about it before. We could have just as easily used A. It's not a big deal. Okay, what were we given? Okay, let me repeat that for the people at home. What was shouted out was 325 milligrams, and I'm going to argue no.
25 milligrams of aspirin?
No.
Milligrams.
Milligrams of aspirin. That's what was given. Okay? And I know that's a silly, stupid thing to complain about because you said that when you said the 325 in front of it, but it's again recognizing the power of the unit. The unit is what's allowing you to do this. Okay? Not the number. Once you've got the unit, now you can worry about the number. Okay? And arguably, I shouldn't have even written the number in yet. This may be the unit that was given, but should that be in the numerator or the denominator? Why should it go up in the numerator? Okay. The measurement unit is mass. What do I want? Mass. Where's the mass unit show up? On top. In the answer, which means where should the mass unit show up in my calculation? On top. What's the substance? Aspirin and aspirin. Where did it show up? On top. Where should it show up? On top. That's why I know that needs to get placed there. There's a logic behind that placement. Okay? If you don't have that logic, that's okay. You might get lucky and just place it there correctly. Okay? That's okay. Okay? Is milligrams aspirin the same thing as micrograms aspirin? So what do you have to do? You have to set up a conversion. And in that conversion, what do we want to happen? I want to get rid of milligrams of aspirin, and ideally, what do I become? Micrograms of aspirin. What's the problem with that conversion? Okay. Most people don't know that conversion. Okay. That doesn't make that a wrong step. You just don't know what numbers to put in there. So if you don't know what numbers to put in there, convert into something else that you do know. Okay. What do you know? Whoops. You know how to go into grams. What is that conversion? Milli means 10 to the negative 3. Where does the power of 10 go? With the, and I don't like base as a word, but you're okay. Core unit or root unit. Which is the core or root unit? Grams or milligrams? Grams. So 10 to the minus 3. What goes on the bottom? The 1. Because I don't want to change that power of 10. If that's any other number, the power of 10 changes. Okay? This is fantastic because my milligrams of aspirin cancels. So I've gotten rid of that bad unit. But at the same time, what have I introduced? A new bad unit. So what do I need to do? I need to convert that one. I need to get rid of grams of aspirin. And ideally, what do I move to? Micrograms of aspirin. Is that one I was required to know? No. So I missed this step with the black conversion. Okay. If you don't know it, what should you do?
Look it up.
Ask a neighbor.
Not quite. Not during a test. Okay. So one option is check the front of the exam. You won't find milligrams to micrograms. Okay. What else could you potentially do? Ask me. You're allowed to ask me. You can raise your hand and be like, I don't know this conversion. Okay. My answer could very well be, I'm not giving it to you. You should know it. Okay. Or you should know where to find that information. And that's probably what I'll give you, is you should know where to find that conversion. Okay. Which means potentially two things in this coming unit. One, you picked a bad conversion, try again. Or two, you're responsible for knowing where to find that information. It could have been in your brain or on the exam. Explicitly, or, this is the next fun one, implicitly on the periodic table. Okay? There is lots more information stored on the periodic table. Okay? This is the whole point of chapter 8, recognizing that that information is stored there. Okay? This one isn't stored there. That one's found. It should be on the exam. I don't know if it's actually on there or not.
I think so.
Okay? This would be raising your hand, you didn't give me this, dude. And I'd be like, yeah, you're right. Micro is 10 to the negative 6. Now what unit would we have? Micrograms. Do our units match? Now that the units match, I can go through and do the mathematics behind this. Okay, kind of makes sense? Okay. Yeah, let's just accept that. Okay, so I just want to throw this out there because a colleague of mine who works with me in English, okay, said that we need to kind of address the value of the mathematics. So if we looked at this conversion, convert 2,437,000 inches into miles. Okay? But your rule, you can only use alphabetic symbols. Okay? So A through Z, no numbers. Okay? How would you set that up? You could try and do some coordination between the letters and the numbers, but then how would anybody know that that's what you were doing? Okay? You'd have to write out the code saying A is 2. Well, if that's the case, you've used a number, and that's no longer alphabetic. What? I had it secretly coded. The other problem with that is then if you wrote out words, what's the problem with the words? The words could then be coded as numbers, which you didn't want. So really what this is asking you to do,
Just to write it out.
What?
It's like that, you gotta make peanut butter and jelly, and you either write out why or how to do it.
see the part in italics up at the top? So this was an exercise done in an English class. They said, okay, do this. I wrote out all the stuff that's not in italics. So what's the extra stuff in italics?
The direction.
I didn't include a thesis statement. So I had to go back and fix it. I was kind of irritated about that. I was like, I spent all that freaking work, and all you're going to tell me is why it's wrong. Okay. It sets up all the steps. If you actually read through that, and we think back to how we've done all our conversions, I've gone through and said that for every single conversion we've done. Okay? And ultimately, all we end up seeing is the mathematical expression, and that's where, oh, you just did multiply, divide, and all that. There was a reason behind that. That sets up the reason behind it. Okay? That's what you should be thinking about when you approach conversions.
That's a lot of words.
It is a lot of words. What's that? Does it use numbers?
But it's written.
Oh, it's
Oh.
It's
They're
written
alphabetic.
and alphabetic.
When I think of alphabetic symbols, I just think of
Yeah.
simple.
So I just put that out there to give you an idea behind it. That's ultimately, every time we do a conversion, that's what we're trying to get through. Okay, just the process of reading that takes like 5-10 minutes, much less comprehending the process. Okay? And that's with units of inches and miles. How many of you understand at least ballpark what an inch is? A mile? Okay, so what happens if we say switched to atoms? Okay, and I'm just going to say you were choking on the whole fact that now you don't know what that means, but it probably wasn't that. Okay, or molecules. We're now shifting to an entirely different system. Why is that system so much harder to comprehend? If I asked you to point to an atom, could you? No. Point to a molecule? No. There's no way for us to physically point out or work with any of these things. We have to use our imaginations to draw these structures and envision what they are and think about them on that insanely tiny scale, and that's difficult to deal with. Okay? So let's take a look at the equation and address something about its strength and potentially its weakness. How many atoms of sodium are needed to make one molecule of sodium carbonate? Okay, so simple little question. What are we trying to do?
Find out how many sodium atoms we can make one sodium carbonate.
I want atoms of sodium in what?
In sodium carbonate.
In molecules, I abbreviate MLCS. Why not write out molecules? It's longer. I don't want to do that. Why not write out just MOL for molecule?
That's a mole.
That means mole. That's an entirely separate meaning. Okay, so I abbreviate MLCS for molecules. What's the molecule I'm looking at? Sodium carbonate. So that's what I want to solve for. So what do I want to start with? Okay, I want atoms of sodium. Okay, and the given information is sodium carbonate, which you're responsible for being able to say Na2CO3, right? That's our nomenclature. So that's our given information. How do I get atoms of sodium from that? And some people are like really hesitant on this, like
The subscript of it.
there's a 2 right there, but Mike's tricky. There's no way that that 2 means there's 2 sodiums in that. That's exactly what it means. That's the power of the formula. The formula tells you how many sodiums there are. There are 2. Okay? And then I want, of course I gave myself no space, so I'm just going to write it underneath. I also want molecules of sodium carbonate. Well, how many molecules of sodium carbonate am I looking at here? How do you know it's 1?
No coefficient.
Coefficient in front. I'm looking at 1 molecule of sodium carbonate. In that 1 molecule of sodium carbonate, how many sodiums are there? 2. There it is. Literally came right off of the formula. Okay? Which is being like, that just seems suspiciously easy. Yes! That's exactly right. It is suspiciously easy. Because it is that easy. That's the point of the chemical formula. It literally tells you those numbers, and it allows you to make those relationships. Okay? So, if you were to be asked something about it on an exam, I could ask you to convert to atoms of sodium from molecules of sodium carbonate. I want to know how many atoms of sodium are in 50 molecules of sodium carbonate. What do you have to do? You need this conversion factor, where molecules of sodium carbonate cancel, and I'd be left with atoms of sodium. And my answer becomes 100. The chemical formula gives you a conversion factor. That's really cool. There's embedded information in it. You have to know to pull that information out. Okay? So that's our chemical formulas. Well, isn't there something more complicated up there? Didn't it say something about the equation concept? How many molecules of sodium carbonate are needed to make 2 molecules of sodium hydrogen carbonate? That's going to be a lot harder. What am I solving for?
Molecules.
Molecules of sodium carbonate.
Sodium carbonate, what am I starting with? Fix that. Fix
Hydrogen, carbon.
molecules of sodium hydrogen carbonate is what I'm starting with. MLCS, NaHCO3. How many of them? 2. Okay. Are the substances the same? So I started to say, well, how many times does sodium hydrogen carbonate show up in sodium carbonate? Does it show up in sodium carbonate? Sodium hydrogen carbonate has what? Hydrogen. Sodium carbonate does not. How many times does sodium hydrogen carbonate show up in sodium carbonate? It doesn't. I can't pull the chemical formula information. So how would I know how to come up with a conversion factor that would allow me to convert those substances? I give you 2 bicycle tires, how many bikes can you make?
2.
Wow, that was awfully fast to tell me 1. How'd you know that? A bicycle has 2 wheels. If I have 2 wheels, so just put it on the frame, which you assumed that I gave you, which could be dangerous, but that's a good assumption. And you make 1. What did you use to come up with that answer? An equation, a chemical equation on how to build a bicycle. How do we convert sodium hydrogen carbonate into sodium carbonate? From a chemical equation. There it is. So I can use the information in my chemical equation. What information is stored up there? I can look at molecules of sodium hydrogen carbonate. Why would I put that in the denominator? So that the units cancel. What do I want in the numerator? Molecules of sodium carbonate. Where do I find the relationship between those substances? I heard a coefficient. What coefficient? Where do I find that coefficient? From the chemical equation. I find that conversion factor by going to the chemical equation. Can I just use any chemical equation? No, good answer, because if the chemical equation I'd given you was this, fat lot of good that does. Why is that a problem? Okay, so we could make the argument of not balanced. We'll get to that. I'd argue there's a larger issue with this equation. We're not looking for water or hydrogen or oxygen. That chemical equation doesn't involve any of the things I'm converting. So the chemical equation I need to use would be the one that allows me to see how those substances are related. Okay? Which then brings in the next layer behind it. I would use the coefficients from it. Okay? But those coefficients must be correct. How do I know the coefficients are correct? I've balanced the chemical equation. Right? So when we initiate this conversion process, you need an equation. You need to be able to balance that equation. You need to be able to recognize that the coefficients from that balanced equation can be used to generate a conversion factor. Everyone's being, well, it's just 1 and 2. It's always just that simple. The issue is you get bogged down behind all the numbers. This is why ignore the effing numbers and focus on the units. The units will help you go through and solve. Kind of, sort of? Okay, so now that we got units, what numbers do we need to pull into it? Okay, so just 1 and 2. What do you mean no? How do you know it was 1 molecule of sodium carbonate?
Because this was given in the chemical equation.
What do you mean it was given in the chemical equation? Keep going. Still don't believe you.
There is no way
Where are you looking in the chemical equation? Yes.
for sodium carbonate.
You're finding sodium carbonate, yes. And what are you looking for?
The coefficient before it.
The number in front. I don't see anything written there.
Where you can
There's an understood 1, good, which then means I could put the 1 in there. What do I do for the sodium hydrogen carbonate? Same thing, I find it in the equation and then look at the coefficient in front. How many of you trust that I actually balanced it? Oh, good, nobody rose your hand. Good job. It is actually balanced, I think. Yeah, I think it's balanced.
It's balanced.
Yeah, it is balanced. Okay, so yeah, I balanced it. Okay? So you have to use those balancing skills. But how did you get the balancing skills? You had to know all your charges so that you could predict the proper products. Okay, so that you could predict the proper reactants. You have to be able to do the nomenclature to get those formulas. So all of these pieces stack. This is why Unit 3 can become more difficult, because you're required to be able to do all that background information and then be able to pull those interpretations out. Kind of, sort of? Okay. So let's move to the next one. What is the mass in grams of sodium hydrogen carbonate produced when 2 molecules of CO2 are consumed? So what am I solving for? Grams of was a good statement. What's the of? Sodium hydrogen carbonate. What am I starting with?
Molecules of CO2.
Molecules of CO2. How many? 2. Okay. What do you notice in this conversion? Units. What about these units? Yes. We're starting with mass, and we're ending with mass, and we're starting with molecules. The measurement unit for molecules is a little bit weird. It's a count. Okay, there are 40 people in this room. Okay, that's still a measurement. I've counted people, but we don't have a unit per se for that, other than calling it individual people. Okay, so we end up really referencing it as the substance. Okay, so that becomes problematic because I have a mass measurement and I have a count measurement. What else is the issue? Yeah, we'll need a conversion factor because the measurement unit is different. What else is the different?
It's asking for CO2.
I started with CO2, and what am I ending with?
CO3.
Sodium hydrogen carbonate. What else did I convert? What the thing is. Okay? I've changed the measurement unit and I've changed the substance. How do we change substances?
Reaction.
Through a chemical reaction. Well, we got the chemical reaction, so that's not a big deal. How do we change that unit? Molecules to grams. Let's try it this way. How do we change molecules to a mass measurement?
Periodic
Okay.
table.
Periodic table. So on our periodic table, we have, because the key says it up there, we have the atomic weight. Okay, what is the unit for the atomic weight? It is not grams yet. It is the atomic mass unit, AMUs. Okay, so that is a mass unit, which we have no way of measuring. It's just the mass unit for an atom. That's why we call it atomic mass unit, AMUs. That's where it's coming from. So we could use the periodic table to figure out the mass unit for a molecule of CO2. So molecules, AMUs. Okay? And in particular of CO2. Okay? This gets a little bit weird. We're still calling it AMU, but does it make sense to call it AMU anymore?
No,
Why not?
because we don't have some.
It's not an atom anymore. Do we still call it an AMU? Yeah. Sorry. Deal with it. Okay. So how would we get the numerics from that? Add up the atomic weights for each of those elements. So carbon is 12. Oxygen is 16. How many oxygens are there? 2. So I would have 32 and 12, 44. 44 what?
AMUs.
AMUs in 1 molecule of CO2. You like the flourish? That was kind of fun. Molecules of CO2 cancel. Cool. I now have a mass measurement. I have 44 AMUs of CO2. What becomes problematic with this? It's not the same as grams. Okay? So let's initiate into the next part of this. Okay, I need to convert AMUs to grams. How many of you know that conversion factor? A few of you have the exam. In fact, I think every single one of you has the exam.
That's not the 1.6.
That's the Avogadro out.
It's not Avogadro's number officially. It's
The 1.66
66.
times 10 to the negative 1.
what, grams?
Yes.
1.661 times 10 to the negative 24th grams is 1 AMU. Okay, and here's where we're going to pause in this whole conversion process. Okay, here's why we're going to pause. even if we multiply that out where it is, okay, we still have a problem because we haven't changed the substance yet. What is the order, ballpark power of 10 order that we're going to have for our mass? Okay, we're multiplying it by 2 and 44, that's 88 times 1.66. Maybe we hit 100 there, so we can drop one of those off, and our ballpark power of 10 is going to be 10 to the negative 23. Okay, because 100 times 10 to the negative 24 is going to be 10 to the 23. Okay? What is the accuracy of our balance? 10 to the negative third or fourth, depending on our balance. I think the ones you guys have are 10 to the negative 3. This is 10 to the negative 23. Will your balance measure this?
No.
No. To give you an idea, we'll attempt this. This may be a really bad idea, but let's give it a shot. So we're saying to get something on that order, I need let's pause the video. That would have to be the precision of my balance. Your guys's was 0, 0, 1. Well, that's just because your class doesn't have fancy equipment. If you move into the next class, we give you fancier equipment. We do actually give you fancier equipment. So the next class is better than you guys. And their balances, that 1 0 was the difference between your balances being about $200 and the next one being 500. And we have cheap balances. Okay? What happens if you add another 0? Now $1,000. Add another 0. Add how many extra zeros? That's a really expensive balance. Can we make a measurement that's at that scale? No. We've got a really big issue here. Yes, we may be able to do these conversions. Fantastic, phenomenal. Can I use those? No. I need something to allow me to scale this up so that I can actually make that appropriate measurement. That scaling factor is a mole. That's the whole point of a mole, is to make this conversion come up with a number that is kind of close to this in blue, not that crappy one in black, because that I can't measure. Okay? That's the power of a mole. Okay? So really it's just trying to wipe out all of those zeros as much as possible. That means when I go through to run the reaction, I can't just use a single molecule or 2 molecules. I have to use a lot more molecules, because in our conversion, that power of 10 must disappear. So that means when I start off, I can't start off with 2 molecules. I might have to start off with 2 times 10 to the negative 24th molecules. Sorry, positive 24th. You can't have fractional molecules. So I start off with a whole crap ton of molecules. That then gets rid of this factor, or makes that factor less impactful, which means the answer I get is no longer this 10 to the negative 23rd. It would then clean that up significantly, and we'd get an answer more like 244, 100. Okay? 100 is still really big, so I probably don't need 10 to the 24th molecules. Okay? But that is now something that I can mass out. Everybody see that? Okay? This is the point of a mole, is to scale my reaction up far enough that I can actually do an experiment. Because if I use the basic understanding of atomic theory, okay, and even the basic understanding of chemical equations, those aren't workable in the lab. I need something else to help me move up. That's what the mole is. It's to change the amount of molecules I'm starting with to be at a reasonable level. Okay. Should I do 10 to the positive 24? Sure. It could be positive 23. Okay. It could be actually the scaling factor. It could be 12 times 10 to the 23rd. Okay, why 12? Well, you're just making up numbers now, Mike, roughly. Why 12? Have you heard of a 12 before? You go to the store, you buy eggs. What do you buy? You buy a dozen. Nobody said you buy 12 eggs. Okay, why'd you not say 12 eggs? That's what a dozen means. Okay, I can scale up by anything I want. Literally anything. The power of the mole is the exact numerical value that I decided to scale up by. The exact numerical value I scaled up by entirely cancels this term.
Yay.
That's why moles are cool. In that process, that simplifies this AMU to molecules thing, and it changes it to now grams per mole. It makes life a whole lot easier. Okay? Kind of makes sense? Okay. So you guys did really well with the formula, so we're going to skip the bike example, and we'll just look at our moles. Okay? So the number that was picked was 6.022 times 10 to the 23rd. Okay? It says atoms. Does it have to be atoms? No. What could it be? Could be what? I heard suggestions. Okay. The best answer that I come up with is items. Okay. So it could be molecules. Molecules are an item. Okay. It could be desk lamps. Okay. It could be pen caps. Okay. Those are all items. Could it be grams? Why not grams? Aren't grams items?
They're unit.
I don't accept unit. What are grams? A measurement. Okay. If you want to do grams, you can do that. You're talking about the physical object of a gram. Not the mass, the physical object of a gram. Okay? To be an item. Okay? That isn't the same thing as mass. You can't do that. Okay? So we're talking about items, not measurements. Okay? And that is a challenging concept. You can't use grams.
Don't you say grams per mole?
We say grams per mole, but is it 6.022 times 10 to the 23rd grams per mole? No. Okay. How many oxygen atoms are in 0.240 moles of O2? How would you set it up? Okay. So I heard O2 on the right and then heard atoms. I'll accept that. You kind of gave that reverse order, but that works. Substance and then unit. Does everybody agree that that's what you're solving for? Does everybody agree that that's what you're solving for? Okay, those of you that were looking at me should have an answer, a solid answer. Is that what you're solving for? No. What are you solving for? How many oxygen atoms? What is O2? A molecule. What are you solving for? Atoms of just O. Okay. This goes back to that diatomic argument. You're like, oh, it's oxygen, so it has to be diatomic. Unless it literally says oxygen atoms, which it does. Okay. So we're solving for exactly O. What are we starting with? Moles of oxygen. Okay. How many moles of oxygen? 0.240 moles of oxygen. What do you notice? What's changed? Freaking question. Yeah, that's true. Okay, so here, we'll write it out really fast. Moles, oxygen atoms, sorry. What do we start with? Okay. Yes, there's a 0 there. I'm going to go ahead and focus on the mole unit, moles of O2. I want to convert it into oxygen. I'm I'm converting the substance and only the substance, which means I'm looking at moles of oxygen. Okay? I don't even need to know what a mole is. All I'm converting is the substance. Okay? How many oxygens are in O2? 2. Okay? I have no clue what a mole is. Completely irrelevant. Okay? But as long as the mole stays the same, all I have to worry about is the formula. Okay? Now what happens? Moles of oxygen cancel. I have moles of oxygen atoms now, which is good, but I want atoms of oxygen. So I need moles of oxygen on the bottom, and I want atoms of oxygen. What is atoms? Oh, because I hit the stupid button. That was supposed to be items. Right? Are atoms an item? Yep. So what can I use? 6.022 times 10 to the 23rd atoms is 1 mole of oxygen. What happens to the units? And I now have atoms of oxygen. Now I can punch into a calculator and I have my answer. Okay, we'll pick up there. Sorry for dropping it and then taking too long to get back to that.